I'm now going to continue my video series on elementary mathematics with a 4th grade Common Core math lesson. And this is in reference to a video entitled Common Core Standards Math Lesson Example, which was uploaded by a YouTuber with the username of Teaching Kids Learn. Okay? So in the beginning of this particular video, they start with this right here, and you have a young kid come up to a dry erase board and start drawing circles like this. Okay, you see the 1 circle, the 2, the 3, and the 4, and so on and so forth. So the teacher asks this kid, okay, the teacher asks this kid what kind of a pattern this is. And what does the kid say? It's a growing pattern. Okay, let me tell you guys something. I am a data processor. I have had lots of mathematics. I have been teaching mathematics for over 3 years on my YouTube channel. Never once have I ever heard of a growing pattern. As a matter of fact, the only time I've ever heard of a growing pattern was in biology. So the first thing I would do is refrain from calling this a growing pattern unless you're teaching something in biology, which in this case you're not teaching anything in biology, so this is not a growing pattern. Now, by the time a kid gets to the 4th grade, he has a pretty decent vocabulary, and it would be no difficulty whatsoever to teach this kid the word ascending. This is an ascending pattern, okay? There are ascending patterns and there are descending patterns. And it would be no difficulty whatsoever to teach a kid the words ascending and descending. That would be no challenge whatsoever to a 4th grader. Okay. Now let's go on here. Then the teacher draws these squares. Okay? And the teacher calls these squares windows. I don't know why they would do that, but okay. And then they call the sides of these squares sticks. Again, I would know no good valid reason why they would do that, but okay. Anyway, the first thing the teacher establishes is that there are 4 sides to the square. Now, how do you draw a square like this? Okay. Well, here's how you do that. First of all, you learn Euclid Book 1, Proposition number 1, which teaches you how to duplicate lines. And then you learn Euclid Book 1, Proposition number 22, which teaches you how to duplicate a triangle. And then you learn Euclid Book 1, Proposition number 46, which teaches you how to make a square. And yes, you can actually make a square with a compass and a straight edge without all the markings of the ruler. It is entirely possible. It's in Euclid Book 1. If you don't believe me, you can look it up for yourself. Alright, so the teacher says, well, there are 4 sides to the square. Then the teacher asks the kid how many sides there are to this. And of course the kid says 7. The reason for that is that these 2 squares right here share a common side. Otherwise, there would be 8 sides. 4 sides for this square and 4 sides for this one. The only reason why there are 7 sides instead of 8 is because these 2 squares share a common side. The same is true right here. Okay? You have 3 squares. This square and this square shares a common side. This square and this square also shares a common side. So instead of having 12 sides, you have just 10. Okay. And then the teacher throws out the term conjecture. Now, what is the term conjecture? Well, if you're going to throw out conjecture, I'm going to throw out a term of my own called etymology. Now, what is etymology? Well, etymology is not to be confused with entomology, which is the study of insects. Actually, etymology is the study of word origins. Now, what is the word origin of this? Well, this is a Latin prefix called con, and it means together. This here, in the English alphabet, you have the letter J. But in the Latin alphabet, you don't have a J, so you have to use the letter I instead. This happens to be a Latin verb, and it means to throw. So basically, the word means to throw together. Now, if you're going with a slightly more modern English definition, you have interpretation, conclusion, or guess. guess is an obscure definition of conjecture. Most of the time it's a conclusion or an interpretation, which means that when you're making a conjecture, you are saying that I see a definite pattern in this. Now here's the problem with that. It is possible that if you start a pattern where you start with the number 4, which, by the way, this is a positive integer, this is a positive integer, and this is a positive integer. So, if you add 3 to this positive integer, you get 7. If you add 3 to this 7, you get 10. Now, if you add 3 once again, you're going to get 13. Now, based upon the pattern you're seeing so far, it is possible to conclude that the next number is 13. But I feel that the kid was right instead of the teacher. The reason why is the kid did not use the word conjecture. The kid actually used the word hypothesis. Now, what is the definition of hypothesis? Let's look at the etymology of hypothesis for just a second. These are Greek terms. In other words, this is a Greek word. Hupo in the Greek means under. This is a Greek prefix. Thesis is a Greek suffix. Okay, this is a Greek suffix, and it means placing. So literally, when you're defining hypothesis, you're placing something under something else. Okay? Now then, the correct definition of hypothesis is supposition. Now, I could have gone on and presented the etymology of the word supposition, and if somebody ever asks me to do it, that's exactly what I'll do. However, in this case, just to save a little bit of time, I'm going to show you that the definition of supposition is an uncertain belief. Okay? We believe that the next number that will come in this pattern will be the number 13. Why do we believe this? Because if you add the number 3 to the number 4, you get 7. You add the number 3 to the number 7, you get 10. So there would be no reason to doubt at this point that if you add the number 3 to 10, it'll be 13. But there's a problem with this. We're not entirely sure that the next drawing that will be made over here will represent 13. We don't know that. Okay? That's what we're guessing, but we don't know that for sure. So the word hypothesis would be better to be used in this particular case than the word conjecture. You hardly ever see the word conjecture in mathematics, but you do see the word hypothesis because it's more specific to this situation than conjecture. Okay? From mathematics, you formulate a hypothesis, you test the hypothesis, and if the hypothesis passes the test, then you have a theorem. And that is more closely related to mathematics than conjecture, because conjecture is a more solid conclusion than a hypothesis. And then more terms are thrown out. The terms of input and output, that's thrown out. Well, let me tell you something. I've been in data processing for years. I have programmed in the languages of the beginner's all-purpose symbolic instruction code, as well as the common business-oriented language. And I have programmed in the formula translator. So, I have also programmed in the hypertext markup language. I have worked with XQuery, I've worked with XML, so I've worked with a lot of stuff. And let me tell you something, you hardly ever see input and output in mathematics, but you do see this in data processing. That is something that you see a lot in data processing. So I would reserve this for data processing terms rather than mathematical terms. Now, the next thing you throw out is the term of function. I couldn't possibly define this as an authentic function, and here's the reason why. Because we don't know for sure that the next number in this pattern is going to be 13. We can formulate a hypothesis that says that, but we can't say for sure that the next number is going to be 13. I wouldn't even go as far as to do that. I can say hypothesis-wise it could be, but I'm not going to say that for certain. So I won't form a conjecture, but I will form a hypothesis. Okay. So what is a real function? Well, if you look through my mathematics videos, and I have a playlist of those, you will find videos that will clearly explain what functions are. But to be brief, functions are comprised of domains and range. Now, what is a domain? Domains are sets of numbers. Ranges are also sets of numbers. But these domains in a function are monogamous. Now, what is monogamy? That's when, well, to illustrate, that's when one human being marries another human being. Okay? Now, polygamy, on the other hand, is when one human being marries more than one human being. Let's say the one human being marries 6 other people. That's polygamy. But if the one human being marries exactly one human being, that's monogamy. So, going by this illustration, we pair up, and I'm going to say it this way. Let's say that these are 2 sacks of marbles. And all these little dots represent marbles, and all these little dots represent marbles. So we're going to marry off. We're going to take 1 marble out of here. We're going to marry it off with exactly 1 marble in here. Now the kick is that these marbles in here can marry as many of these marbles as they like. But the same is not true with these. These have to pick 1 and only 1 marble in here. Okay? So 1 number of the domain is matched with exactly 1 number of the range, even though 1 number of the range can be matched with as many numbers of the domain as it likes. You say, well, I'm still confused. Let's say the number 2 was in the domain, and let's say the numbers 5 and 6 are in the range. Now, we will pair off the 2 and the 5. Okay? Now the thing is, 6 can marry 2 also, but 2 can't marry 6. You say, well, doesn't that contradict itself? Well, kind of, sort of, but I think you're finally getting the idea. If this was choosing between these 2, it'd have to choose one or the other. But 6 can marry anybody. Okay? 6 can marry 2, and let's say there is a 4 in there. So 6 can marry both 2 and 4, but 2 could only marry 5 or could only marry 6. So 6 could actually be married to 2, even though 2 is only married to 5. Might seem a little confusing, but if you go through my mathematics videos, you'll see all this for yourself. Okay. Now then, as far as I can tell, I've pretty much covered everything in this particular video. If I missed something, let me know. In the meantime, as a conclusion, I'll say this is an ascending pattern. You form hypotheses in mathematics. You rarely ever form a conjecture. And the term function in mathematics is represented by the f of x. Okay. So sometimes you'll see like y equals x squared. Well, in this case, you'd replace the y with an f of x. Okay? Anyway, hopefully I unscrambled your brain a little bit. Hopefully you'll look up all those Euclid proofs. Remember, we're talking about Euclid's Book 1 proposition number 1, Euclid Book 1 proposition number 22, and Euclid Book 1 proposition number 46. That's how all these squares got formed. And they got formed without a ruler too. Alright, I've talked too much as it is. I will tell you more in a future video, so stay tuned.